So this is the so-called harmonic series. Why it's called the harmonic series, you can do your own research on that. I know a music teacher once told me something about a string, maybe that long, vibrating. So the string comes out this side and this side, so it's like a wave motion, and it's making a sound. And they said something about harmonics. If you take integral parts of that, like say half, so divide into two parts, and it can oscillate out there backwards and forwards, making two waves for the same length. And there's certain sounds it makes, and they call them harmonics of some description. So you could make three. So there's a node there, and a node there, and a node there, and so on. And that same length of string, if you were to third it, you could get this little guy oscillating that's a third of the length and making a certain sound relative to the big one, and somehow that's harmonics. Well, this is the same case. We've got a half and a third and a quarter and a fifth. So it's the harmonic series. And of course, they're totally to do with waves. So later when we do simple harmonic motion, of course, we'll be looking at some sort of waves as describing the motion, and sine and cos are going to feature in there. This harmonic series is interesting because, of a few things. Firstly, does it have a limiting sum or not? Because we know our old friend 1 plus a half plus a quarter plus an eighth plus 1/16, ... We know that guy does have a limiting sum. It's a geometric series, and its common ratio is a half. So you times by a half to get from one term to another. So if the common ratio is a half and the first term is 1, then we know we can find the limiting sum, A on 1 minus R. And the limiting sum for this particular series is 1 on 1 minus a half, which is 2. So this series does have a limiting sum, but does the one above it? And we've explored that when we did our work on inequalities. We looked at, you could look at integrals. You could look at the integral of 1 on x. Maybe use an integral test, which I don't want to go into particularly now, but that integral there, if you go from here at 1, so this is y equals 1 on x, and you look at the area that's out that way, that goes forever. The area just increases without bound. If you were to integrate, you would know that the integral of 1 on x is natural log of x. And as you go out there, there's always going to be a value for the natural log of x. So we're getting an area that unfolds. It unfolds more and more slowly, but it is actually increasing without bound. And if we took, say that's 1, 2, 3, 4, if we made some rectangles here, then we could see that the area of each of these rectangles will correspond to our series above when we add them together. For example, this first rectangle is a 1 by 1 rectangle. 1 times 1 area is 1. The next one is a half times 1, because this value in here, because the curve is y equals 1 on x, that's 2 comma a half, so the height is a half. So this is 1, that's a half, that's a third, and a quarter, and so on. So if you added up all the rectangles out to infinity, you'd be getting that sum. And that's bigger, because you can see the rectangles are above, they're the upper rectangles. That's bigger than the actual integral, which we know the integral is unbounded. So something that's bigger than the integral clearly is unbounded. So we could look at it from that point of view. Another way that we looked at it when we worked on our inequalities was to actually do some replacements. So this original series here, we could actually say, how about we replace the third with something that's smaller than it, a quarter. And how about we replace the fifth and the sixth and the seventh with something that's smaller? And how about we replace the 9th, 10th, 11th, 12th, 13th, and 14th, and 15th with something that's smaller? If you replace it with something that's smaller than it, well, clearly you're getting a series now that's smaller than the original. So, well, I've got another 8 there to add into it. And I've got a 16th to add into there. And I've got a quarter to add into there, and a half there, and I've got 1. All right, so this new series I've created in red is smaller than the one above it. But the new series that I've created is 1 plus a half plus a quarter and a quarter, which is a half, and an eighth and an eighth and an eighth and an eighth, which is a half, and a 16, 16, 16, 16, 16, 16, 16th, and a 16th, which is a half. So I've got 1 plus a half 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 going out there, which clearly goes without bound. That sum of that series goes without bound because you're always adding on a half. And it's smaller than the original series, so clearly the original series must increase without bound because it's even larger, right? So that's one interesting thing about the harmonic series. It increases without bound, and in our work with inequalities, we looked at those couple of things about it. Another thing that is interesting is the harmonic mean. Now, the harmonic mean is actually the flip of the mean of the flips. I'll just write that down. It's how I remember it. It's the flip of the mean of the flips. Take any 3 terms, the middle one in there will be the harmonic mean of the inner and the smaller and the bigger of the 3. Let's just pick 3 terms. An eighth, a ninth, and a 10th. There's just 3 terms in the harmonic series, and we're saying that this guy is the harmonic mean of the 8th and the 10th. A 9th is the harmonic mean. Now, how do you find the harmonic mean? You find the flip of the mean of the flips. Okay, let's find the mean of the flips first of all. So we're talking about an 8th and a 10th. What's the mean of the flips of those? Well, the flips of those is 8 and 10, and the mean of that is 8 plus 10 on 2. 18 on 2 is 9. But I want the flip of the mean of the flips. So I will get 1/9 if I flip that. So if I find the flip of the mean of the flips, I'll get my harmonic mean. Another way to write that is, say you have 2 numbers A and B, the harmonic mean would be where you get the flip of the mean of the flips. So you actually want to find 1 on A plus 1 on B and divide by 2 and flip it. So you would get that, which we know we could re-express if we decided to do some fraction work as 2AB on A plus B. So that would be a formula. For the numbers A and B, 2AB on A plus B, which means if I did it this way, 2 times 1/8 times 1/10 on 1/8 plus 1/10 would get me the answer, right? So that's 2 times 1/8 times 1/10 is 2/80, 1/40 on, and that's 10 plus 8, that's 18 80ths. So we get a 40th on 9/40ths, which is 1/9. So that's interesting. The harmonic mean is the flip of the mean of the flips, or 2AB on A plus B. It's a type of mean. There's, as we know, it's not just the arithmetic mean that exists. There's the geometric mean, and now there's the harmonic mean. What's the harmonic mean useful for? Well, what about if we went up to the top of Mount Alexandra from here? It's uphill, so on our way there, we go a bit slower than on the way back. So let's say John walked to the top of Mount Alexandra at a speed of, it's uphill, so let's go at 2 kilometres per hour. He returned at a speed of 4 kilometres per hour. I wonder then what the average speed for the whole journey is. What was the average speed for John's entire journey? Now, the harmonic mean is a totally good use for that. When we're working with rates, the harmonic mean is a good thing for averaging out rates. So I'm saying you should find the flip of the mean of the flips and you'll be done. So 2, if I flip that, I get a half. 4, if I flip that, I get a quarter. If I find the mean of those flips, what's the mean? Well, half plus a quarter is 3 quarters. So that is equal to 3/8. But I want the flip of the mean of the flips. So it'd be 8 on 3, right? Which is 2 2/3 kilometres per hour. 2 2/3 kilometres per hour was the average speed. Some people go, but it was going at 2 kilometres per hour going up and 4 kilometres per hour going down, so wouldn't it be 3? That's halfway. But remember, he spent longer going up because he's going slower, and he was quicker coming down. So he didn't spend as long going at the faster speed. So the average speed is actually dragged down a bit from being halfway between those two speeds, from being 3. It's 2 2/3. Now, you could have done this question the long way. You could have let the distance to the top of Mount Alexandra be d, and you could work out the total distance travelled divided by the total time. We know that speed is distance on time, so time is distance on speed, right? So the time to get to the top of Mount Alexandra, I'm going to call it T1. T1 is equal to the distance divided by the speed going up. And the time taken to come down from the top to the bottom, I'm going to call it T2, is the same distance going up or coming back, but divided by 4. Time is equal to distance on speed. So the total time will be d on 2 plus d on 4. And the total distance is just d plus d. It's 2d. So the average speed, right, for the whole journey is 2d, the distance that in total happened, divided by d on 2 plus d on 4. Now we can see that this will be equal to 4d plus 2d, 6d on 8. So it's 2d on 6d on 8. And when we simplify that, we get 16d on 6d, which is just 8 on 3, which we've already got before. So you can work it out the long way, but the harmonic mean is quite useful for averaging out rates.